Yes, hello everyone. It's so nice to be here and get the opportunity to speak here in front of you all. So the topic of my talk today is quantum annealing for ticket control. So I will go into that, but before we do that, a little bit about myself. My name is Aleksandar Davidov. I work as a data scientist at a company based in Norway called Ruter. I will go more into detail about what we do a little bit later. But yeah, I'm a data scientist, as I said. And besides data science, part of my responsibility at Ruter is also doing R&D. Specifically, I work with quantum computing research and development. And I've been leading Ruter's quantum computing efforts since it started around 3 years ago. And I've been also participating in all of the 3 projects we have been working on. I'm very glad and happy to be here at the D-Wave's Qubit conference. It's exciting to be a part of a community pushing the boundaries of what's possible with quantum technology. And equally exciting to share our own experience and insights with others driving the field forward. So, what can you expect from this talk? First, I'll give a brief introduction about Ruter, what we do, our mission, and why quantum computing has become relevant for us. Then, I'll walk you through 3 of our quantum computing projects, all of which use D-Wave's quantum annealers. The first one is about predicting passenger capacity in our tram, metro, and bus systems. The second one is optimizing vehicle allocation for our on-demand transport service. And the third project, which I'm also going to spend the most time on, is a large-scale data-driven optimization problem about how to guide fare inspectors to the right stations and routes to maximize efficiency and impact. Along the way, I'll also show you how our quantum approaches compare to classical solvers and briefly mention the innovation award we have received for our work. By the end, I hope to give you all a concrete picture of how quantum computing, especially when paired with classical methods, can help solve large-scale problems in public transportation. So, about Ruter. Ruter, as I briefly mentioned, is a public company in Norway. We are the public transportation authority in the entire Oslo metropolitan area that is covering the capital and also the surrounding regions. You can think of us as a mix between a transit planner and a system coordinator. We do not operate the vehicles ourselves, but we are responsible for designing the entire public transportation network, setting routes, schedules, and making sure bus, trams, metros, ferries, and even some regional trains work together as one integrated system. We also have an integrated ticket system for seamless travel across all of these modes. Our mission is to make public transport so efficient, reliable, and sustainable that it becomes a natural alternative to private cars. To achieve this, we are not just maintaining the system, we are constantly looking ahead. As part of our research and development efforts, we are starting to explore quantum computing, especially for large-scale optimization problems like vehicle allocation, scheduling, and fare inspection planning, all of which I'm going to talk later about. While classical approaches still dominate our day-to-day operations, we believe that quantum methods have the potential to push current computational limits, and we want to be ready when that tipping point comes. So, now that you know a little bit about Ruter and what we do, let's zoom out for a little bit and look at how people in Oslo actually move around the city. So here, you see a chart. It's the model split of Oslo. In other words, how people get from place to place, no matter if they're going to work, to school, shopping, or just doing something in their free time. This data right here is from 2018, so it might be a little bit outdated, but it's still relevant. As you can see, public transportation makes up a significant share, 34% of all trips. That's much higher than most American cities or Canadian cities, where the transportation usage is typically in the single digits or low tens. Walking is also very common, equal to car usage. Bicycle and other modes of transportation make up the rest. This strong emphasis on shared and active transport reflects Oslo's sustainability goals, and it's the key reason why we at Ruter are investigating in better planning tools, specifically quantum computing. So, now, let's start looking at the first of the 3 projects I'm going to present to you today. So the first one, as I briefly mentioned in the introduction, is about passenger prediction. Then I'll go over to vehicle allocation, and lastly, ticket inspection, which I will also spend the most time on. Going on with passenger prediction. So one thing we noticed is that passengers care about how crowded their public transportation vehicle will be. So in this project, what we attempted was to combine quantum computing with artificial intelligence to predict the occupancy level, whether a bus, tram, metro, etc. is likely to be crowded, a little crowded, or not crowded at all. Each vehicle in our system has sensors mounted above the doors that register how many people get in and off the vehicle. We combine this data with things like the time of the day of the week, and patterns from previous weeks. That gives us a pretty good picture of how full a vehicle tends to get. The model we trained gives us predictions up to 3 days in advance. As I said, it performs a 3-class classification of crowdedness level. Again, if it's not crowded, crowded, or a little bit crowded. This is what we wanted to explore in this project. Specifically, what we wanted to explore was if quantum computing could help machine learning improve the predictions, not by changing the machine learning model itself, but if it could aid it or help it in a way that we could better utilize the data or tune its parameters. So we tested a method where the quantum computing helps decide which combinations of parameter and data gives the most reliable predictions. This is a hard task because there are so many possible ways to configure the model and combine the inputs, and we wanted to find the ones which actually help it make the decisions. That's where quantum computers came in. It helped us search through those possibilities more efficiently than we ever could with classical methods alone. In the end, we noticed an improvement in accuracy. It was small but measurable, and that's actually what matters, especially when you're delivering these predictions to tens of thousands of people every single day. In the end, the version we use in our own ruter app does not use this approach. It's classical. But this experiment gave us a better understanding of where quantum computers can add value, not by replacing what we already do, but by supporting and improving in specific areas which are hard to optimize classically. And here is a screenshot of our app. It is very similar to Google Maps in the way that if you want to get from point A to point B, it gives a route suggestion. And what you can see on the lower corner is that it says usually not crowded. So for this particular trip, the tram here is not crowded. To have these options, let passengers anticipate how busy a trip might be before they board. So if they'd rather avoid a crowded vehicle, they can adjust their plans accordingly. Now let's move on to the second project, which is our on-demand vehicle allocation. This one focuses on our on-demand minibus service, which is quite different from regular public transportation. These are small vehicles that pick up people up directly from their homes. Specifically, this service is meant for older adults and pensioners. And then these minibuses take them to where they need to go. This service runs from the morning to the evening, and it has to be flexible since demands change from hour to hour and from one area to another. The challenge was to figure out how many vehicles we need at each time of the day, and more importantly, where to place them. We wanted to make sure no one is left waiting, but also avoid not wasting resources on having too many vehicles idle in the wrong places. We looked at this as an optimization problem. How do we assign the right vehicles to the right pickups at the right time, while keeping routes short and avoid overlap? It's a tough problem, because the number of possible combinations become enormously very quickly. To handle that, we build the entire solution as a quantum project from the ground up. We framed the project in a way that it fits perfectly on D-Wave's quantum hardware, using something called a QUBO, or quadratic unconstrained binary optimization formulation, which is the format we needed to run this on D-Wave's quantum annealers. We then used real-world data, which includes pick-up points and drop-off points, time windows, and also service constraints, and ran it through the quantum solver. This was done after setting up the full problem and algorithm. The quantum annealer helped us explore a huge number of possible setups, which vehicles should go where, at what time, to cover demand while minimizing waiting times and unnecessary driving. Of course, the quantum solver doesn't guarantee the perfect answer in every single run, but what it does do really well is rapidly narrow down the search space and return high-quality solutions that respect all the given constraints. That's incredibly useful when you're trying to build a responsive system that needs to adapt throughout the day, whether it's a quiet hour or a surge of new requests in a specific area. The results have been promising. Quantum computing gave us a way to test and compare different vehicle placements much faster than traditional brute force methods would allow us to do. And while the project is still ongoing, it shows real potential for making on-demand transport more efficient, both for passengers and for operators. The goal is simple: keep people moving, reduce idle time, and make sure no one is left behind. And with the help of quantum optimization, we're getting closer to achieving that in a smart and scalable way. Let me now show you how this looks like in practice. Here you see Oslo divided into regions. These regions are not manually chosen, but generated by our model. In order to improve how vehicles are assigned across the city. These are the zones it identifies as useful for decision-making. On the left side is the predictive demand. How many ride requests we expect in each region. On the right side is the actual demand, what really happened. The darker the shade means the higher the request. The comparison matters because it shows where the model performed well and where further adjustments is needed. By refining the model over time, based on this feedback, we improved our ability to place vehicles where they actually are needed, even as demand shifts throughout the day. This feedback loop makes the system more adaptive and reliable, which is critical when serving older adults who depend on it. Now, moving on to the last project, ticket inspection. So this is the main project I want to present to you today. And for those of you who don't know, unlike closed systems where you tap through gates or barriers to enter a specific tram or metro, we at Ruter use an open, trust-based system that makes travel easier and more seamless for passengers, but it also means we have to be smarter about how we do inspections. There's no physical checkpoints, so the only way to ensure people are paying is through well-planned, fair, and visible ticket control. But why does this even matter? Fare evasion might seem small on an individual level, but when it adds up, it can put real pressure on public budgets. Even small increase in evasion can force tough choices. Raising ticket prices, cutting services, or relying more on subsidies. And beyond the financial impact, there's a social side too. If people feel the system isn't being enforced, trust starts to erode. This can lead to even more rule breaking or just a general sense of the system being unfair. Traditionally, inspectors were focused on critical stations during rush hours. It makes sense from a revenue point of view. But this approach does not cover the whole transportation network. Some areas get overlooked completely. Worse, passengers can feel singled out or unfairly targeted, especially if the checks always happen in the same places or at the same times. At Ruter, we believe that ticket control should be both effective and fair. That means spreading inspections across the full network and planning inspection routes carefully, so that we avoid unnecessary overlaps, keep travel times short, and make sure that no group of passengers feel targeted. To do that, the first step is to identify where fare evasion is happening, what we call critical or high-risk stations. But instead of just sending all of our inspectors there, we use that input to guide a broader, balanced inspection strategy. We want full coverage, not just hotspots, without wasting time or duplicating routes. This project is about solving exactly that, finding an inspection strategy that optimizes for coverage, fairness, and efficiency. And of course, we turned to D-Wave's quantum annealers for that. Now let's look how we actually built and solved this ticket inspection problem. We started with historical data, specifically past fare evasion observations across all our stations on our bus, tram, and metro network. From this, we estimate a kind of risk level which we associate with each station. This indicates how likely fare evasion is to incur at that particular station. We don't publish these numbers publicly, but we do label which stations are considered high risk within our model. Of course, this helps us focus inspections more heavily where fare evasion is a real problem, while still ensuring that no area is completely ignored. Everyone should see that inspections are active across the whole system, not just a few places. To control that balance between fairness and focused coverage, we introduced two parameters in the model, alpha and beta. Alpha sets a minimum amount of attention that high-risk stations must receive. Beta adjusts how inspections are spread across the rest of the network. If we want to focus almost entirely on high-risk stations, we lower beta. If we want more coverage, we increase it. This balance is crucial. If we only inspect hotspots, we ignore the rest of the city and risk creating a feeling of unfairness. But if we spread inspections too thin, we'll lose effectiveness. So these two parameters let us tune the strategy depending on our goals, whether that's strict enforcement or broad visibility. All of this gets turned into a Qubit model, which I mentioned is the mathematical structure suited for quantum annealing. The challenge here is not just picking which stations to visit, but also making sure that full inspection plan respects capacity limits, how many stations can be covered in a shift, and how the effort is split between high and lower risk areas. As the network grows and more constraints are added, the problem can become too large for traditional methods to solve efficiently. This is where quantum computing comes in. The quantum annealer searches through a huge number of possible inspection plans quickly, respecting all the rules we have set, including fairness. It doesn't always find a perfect solution, but it often finds very good ones, and it does so fast, even as the problem gets more complex. By selecting which stations to visit, that's only half of the battle. We also need to make sure that these plans are realistic. Inspectors have to physically move between stations in real time. That's why we bring real-world timetables. We check that each step in the inspection plan can actually happen. If an inspection needs to be at station A at, let's say, 9:15 a.m., the model verifies whether it's even possible to get there using real transportation connections, whether bus, tram, or a short walk. If the timing doesn't work, the plan is rejected. To make all of this scale, we use a hybrid solver, a mix between a classical and quantum methods. Some parts of the problem are solved classically, while the more computationally intensive parts, the one which involve thousands of decisions, they are run through a quantum annealer. This keeps the solving fast and also lets us scale up to larger networks with many stations, inspections, and time windows without the process slowing down significantly. That speed also allows us for dynamic updates. If there's a change in fairavation patterns, like a new hotspot, or if weather events, schedule changes affect where inspection should go, we can quickly rerun the model and generate an updated inspection plan. This kind of responsiveness is hard to achieve with traditional planning tools. In our tests, based on data that mirrors the Oslo network, the model consistently produced strong inspection schedules. Whether it outperformed classical methods or just matched them, the quantum solver found solutions faster, especially as the problem size grew. And because we're optimizing both station coverage and routing together, we get results that inspections can actually follow and use in the real world. At the end of the day, this project tackles two hard problems at once: deciding where an inspection should happen and planning how to get the inspectors there on time. And it does so in a way that respects fairness, adapts to change, and scales with the system. This map shows a simulated output of our fair inspection strategy across Oslo. Each blue circle represents a station where an inspector is scheduled to visit, and the size of the circle reflects how heavily that station is prioritized, either due to higher prediction fair evasion or strategic importance for coverage. To avoid revealing much sensitive information, this example is based on synthetic data. It's designed to illustrate how the model works rather than show an actual inspection strategy. Also, for simplicity, this version only shows stations in central and eastern Oslo, not the full network. You can't really see it directly, but the model doesn't just focus inspections on the highest risk areas. It also distributes them across the entire coverage region, including outer stations to avoid blind spots. The goal is to strike a balance, focus more where fairavation risk is higher, while still maintaining presence in other parts of the system. This slide shows an example of a route through central Oslo, which is generated by our model. Each blue circle is a station selected for inspection, and the colored line shows how the inspections get from place to place: by tram in blue, bus in red, or on foot in black. The important part here is feasibility. The model only selects routes that work with live timetables. So if a transfer between two stations isn't possible, it won't be included. Each leg of the trip is timed to fit within the shift. Minimize idle travels and respect capacity constraints. The results are realistic, efficient route that still covers a mix of stations from higher risk areas to also more peripheral ones. And balance, the solver uses real schedule data. And that's because the solver uses real schedule data. The plan can quickly be rerun if something changes, like delayed tram or shift in passenger demand. This step turns inspection schedule into something operational, one that inspectors can actually follow on the ground. Now, let's also look at performance. This chart compares how long it takes for two solvers, Gurobi in blue, and D-Wave's hybrid CQM solver in orange, to solve a ticket inspection problem of increasing size, measured by the number of variables on the x-axis and the time it took to run the simulations on the y-axis. Gurobi is one of the most trusted commercial solvers for optimization, so it serves as a strong benchmark here. The tests shown are in range where we believe both solvers were able to find optimal or near optimal solutions. So we are not just comparing performance beyond what each tool can realistically solve well. What we can see is that at lower sizes, around 1,000 to 2,000 variables, performance is quite similar. But once we pass that point, Gurobi's solve time grows much faster, eventually exceeding 350 seconds. By contrast, Leap Hybrid CQM handles the scale more smoothly and ends up being nearly twice as fast in the larger cases. And importantly, this speed improvement doesn't just come at the cost of quality. Both solvers produced solutions of similar standards. That means that the hybrid approach gives us a practical way to scale up larger scheduling or routing problems without hitting a computational bottleneck. So now, before we conclude, I also want to mention briefly about the innovation prize. So in November 2023, Ruter received the Innovation Award from the Research Council of Norway, a national prize given to public or private organizations that achieve innovation through the strategic use of research. Two of the main projects behind that recognitions were the one we just discussed, or quantum-based ticket inspection work, and the development of our own large language model. The model was the first one fine-tuned specifically for the Norwegian language, and at the time of its launch, it achieved the best benchmark scores in the language. Of course, newer models since have surpassed it, as the field continues to grow quickly, but it marked an important early contribution in this space. The award acknowledges our broader commitment to research-driven development, and we see that it also encouraging keep pushing the boundaries of what's possible in public transport. So with that, what we've seen is how quantum computing is helping us tackle real high-demand challenges in public transportation, whether it's predicting vehicle crowding, managing on-demand minibus fleets, or designing fair and efficient ticket inspections. These aren't just experiments, they are applied projects aimed at improving everyday operation for the passengers. What ties them together is the combination of classical and quantum methods. We are not replacing what already works, we are building upon it. And even small, well-targeted improvements, like better parameter tuning, faster solve times, or smarter plannings, can make a meaningful difference at scale. The recognition we already received for this work has been a strong signal that we are on the right path. It reinforces our commitment of using advanced research to make public transportation more efficient, more responsive, and more fair. We're still early in this journey, but we're confident in this direction. And we are excited to keep pushing forward, unlocking more of what quantum computing can offer in the years to come. And with that, I want to thank you all for your attention.